In this lecture, I want to actually go into the practical aspects of Newman projections. That is, when we're tasked with having to use Newman projections, how do we go about starting from scratch when we have a molecule of interest? How do we get to that final Newman projection? So really, just to recap what we're trying to do here, there's nothing super magical about a Newman projection. It's just a way of drawing a molecule so that you can see the 6 groups attached to 2 carbon atoms that are bonded to each other and seemingly undergoing free rotation. And that's why the free rotation aspect is why you would ever want to draw a Newman projection. Otherwise, we'll just stick to bond line structures with wedges and dashes, right? Okay, so let's say we've got, let's make it as hard as possible, which really isn't that hard when we break it down. Let's say we've got this molecule, 2 carbon atoms, and I'm drawing it as a seesaw structure where the straight line that's connecting the 2 carbon atoms is parallel to the bottom of the paper. What I'm going to do is have a group A sticking up and to the left, then B, that's not boron, it's just some variable group. Let's make H. I like H better than C for this example, right? Otherwise we have too many C's. So we have ABH, and then D, E, and F. Okay, now what I want to do is convert this molecule to Newman. So what's the goal here? The goal is to draw the above molecule as a dot with a circle and then attach A, B, H, D, E, F appropriately. We've got our 6 groups. I really like this example, and I say it's as hard as it gets because, yes, molecules could get bigger, but what we do is we take the molecule, we decide what bond we're going to analyze, which bond we're going to care about undergoing free rotation, and then we, from there, draw a Newman projection, and whatever is attached to the dot carbon, for example, we're going to just draw it as is. So if it's like a 6-membered ring, we just draw a hexagon hanging off at position A. If D is like a big Herculean molecule, we just draw it out as best we can. We just like copy and paste and move it over. Try to make the image simple. The focus is on the relative position of the 6 groups that are attached to the 2 carbons, in this case carbon atoms, that are undergoing free rotation. Okay, that's what we care about. So I've got my seesaw structure, and I'm going to draw the above molecule. And I always start with a dot with a circle around it, true, but the first thing I want to do is at the seesaw structure, add your eye. Now, that's kind of a weird phrase. My eye is this, and it could be looking in either way. We assume we have both eyes, and they're looking in the same direction. So we add our eyes to the image, so we add our eyes to the image, and then that tells us what direction we're looking. Okay, so it tells us what direction we're looking, which is important for establishing what's the front atom and what's the back carbon atom. So it establishes the dot and the circle. So back to our original drawing, and I'm going to draw this a few times. So back to our original drawing. What I'm saying is that let's consider what direction we're looking down. Maybe, well, you know what we did was we looked We looked that direction last time. So I'm going to have my eye over here. So I have my one eye that's looking down the bond this way. So our eye is starting at the right and it's looking, excuse me, it's starting at the left and it's looking right. That's an important observation. It's spelling here. Okay, so we're looking right. Why? Well, if you look at the arrow is moving from left to right. It's looking right. It's reading right, however you want to say it. What that means is that the ABH carbon is going to be our dot and the DEF carbon is going to be our circle. So now we draw dot with, about dot and circle with the vertical groups. I feel like I misspelled that. Okay, I gave it my best shot. So with the vertical groups, what do I mean? So we have a dot, we have a circle. That's step one. Now step two is we need to draw the vertical groups. So the vertical groups are our straight lines. And they're the straight lines in the seesaw structure. Okay, so what are our straight lines? Well, our eye travels into the dot, which is the front carbon, that's our dot. And what is the straight line? Well, B is a wedge, so that's not it. H is a dash, that's not it. But A is a straight line and it's up. So I'm going to draw a straight line up to A. Okay, now I'm going to keep moving down, moving through my bond. I'm moving past the carbon-carbon bond that I can't see because I'm drawing a Newman projection. And I'm now into the circle carbon. All right, which of these is a straight line? Is it D? No, D is a wedge. Is it E? No, E's a dash. It's neither the wedge nor the dash. It's the straight line, which is F. And F is pointing straight down. So I'm going to draw a line connecting F, which is pointing straight down, to my circle. Oops, I connected it to the dot. Remember, we want to stop at the circle. Now we've shown that A is connected to the dot and F is connected to the circle. Okay, that's part of the identifying the vertical groups, but we also showed them in their correct orientation. A is up. As our eye ran into the dotted carbon, it saw that A was pointing up and F was pointing down. Okay, so we've now drawn the two groups that are vertical. So then what we do is we add spaces for the remaining four groups. And this is something that I do because it makes sure that my Newman projection is fundamentally correct. That is, what I'm saying, if I have a dot in a circle and A is pointing up because it's vertical up, F is pointing down because it's vertical down. All right, I now know enough about my Newman projection that I know that on the dot, I'm going to have a down and to the left, a down and to the right position. And on the circle, I'm going to have an up and to the right and an up and to the left. Because again, we need to maintain 120 degrees separation between any two groups on the dot and any two groups on the circle. Now I know it's truly 109.5, but based on this perspective, it appears to be 120 degrees. Now this is a fill in the blank question, okay? What we're going to do now is, now that we have our molecule in front of us again, we need to fill in the blank. I believe that's step 4. Fill in the blank, it's blanks, with the remaining 4 groups. Okay, the remaining 4 groups. And here's the idea. The final answer has no blanks. No blanks in the final answer. Okay, so we go to our Newman projection. Dot with a circle around it. The dot has A up. I believe we have F down. Okay. So what we have to do now is figure out where to put B, H, make that dot nice and big, D, and E, right? Those are the remaining groups. We need to put those at the corresponding positions that are remaining in our Newman projection. So how do we do that? Well, we could first of all rotate the molecule around in our mind. We would have to kind of spin it 90 degrees horizontally on its axis, and I believe that's clockwise. So I've been doing this about 15 years now. So rolling molecules around in my mind is something I've been thinking a lot about, but it's not something you've probably been thinking about. The more you think about it, the better. I encourage it, but people will pay you money, hopefully more than me. Anyway, the issue is that's hard to do. So maybe there's a little mnemonic, and indeed there is. So if you're looking left, I'm kind of asking a question. Looking left, if you're looking left, wedges are on the left. Looking left, wedges on the left. And conversely, if we're looking right, again, that's a question, wedges on the right. So what does it mean to look left and look right? Well, that comes down to where our eye was in the original drawing. So looking left was what we did in the first example of a Newman projection in the last lecture. Our eye is on the right side, but it's looking to the left. Look at that arrow coming out of the pupil. It's pointing from right to left. It's moving towards the left. And if it's looking left, our wedges are on the left. So these are really important mnemonics. Now, our particular example, we're looking right. Our eye, the arrow coming out of the pupil, is pointing to the right. Okay? So that means our wedges are on the right. Well, on the right of what? If we go back to our Newman projection, don't overthink this. If we go back to our Newman projection, I'm going to slice right down the vertical substituents, and I'm going to make note that on the left side of my vertical substituents, well, this is just the left side. And this is the right side of my Newman projection. So now I can connect these things where after I cut it in half, I've got, we've got a right side. And then if we happen to be looking left, we're not. I'm just going to highlight this momentarily. There's the left side if we were looking left. We're not. We're looking right. So I'm going to delete that highlight over the. Now what this tells me is that since I'm looking right, my wedges are on the right. The right of what? The right side of my Newman projection. So I now know what to put here and here. These are the two groups that are on the right side. Okay, let's go back up to our structure. We're at our seesaw structure. And what are the wedges? The wedges are B and D. They're the things that are attached by wedges. So B and D go on the right side. So we've got two groups that we need to add to two blank positions. How do I add them? Well, if we go back up, B is attached to the dot, right? It's attached to that carbon that's the first carbon that our eye bumps into, whereas D is attached to the circle, the second carbon that our eye bumps into. So B goes here because that is on a line that is connecting to the dot, right? And then D goes here because that's on a line that's connecting not to the dot, but stopping at the circle. So now we've added our wedge groups. Well, what about our dash groups? Well, our dash groups are just in the final two places on our Newman projection. And that's going to be H and E. Now I'm not looking left, so I'm not going to use that terminology. The eye defines what direction you're looking in. I'm not going to use the looking left wedges on the left. These are dashes, okay? They just go in the last spot. And my dashes were the H and the E, where if we look up at our drawing here, we see that H is connected to C and E is connected, excuse me, H is connected to dot and E is connected to circle. So H is connected to dot. It's going to be attached to that position where the line extends all the way into the dot. And then conversely, E is going to be attached to that line that stops at the circle, implying that it's connected to the circle. So that's an example of drawing a Newman projection from a seesaw structure, which is something that you'll be asked to do on the exam. And in general, I would say people make this a lot harder than it needs to be. If you practice this example here, you should be able to get it for almost any situation. There are just a few caveats that can be handled by just practicing more that really aren't too bad. This is as hard as it gets, though. I mean, you could have an eclipse geometry, something like that. Let's go through two examples really quick. So now I'm going to actually use real molecules where we don't have variable positions. And I'm going to say, convert to Newman. We'll have two examples, sort of real world practice, I guess. Okay, so in the first example, I'm going to consider this molecule. Just coming up with this on my own here. Okay, this is a really practical example. Now what I've done for us is I've drawn the seesaw structure where I now have my bond of interest. This is parallel to the piece of paper. What I want to do in this example is draw my eye on the opposite side. So I'm going to kind of come down here, and that eye is going to define the circle and the dot. So I have my dot with my circle. Now step one was to draw a dot with a circle and add the vertical substituents. So the first vertical substituent I bump into is a C with 3 hydrogens, and then the second vertical substituent I bump into is an H. If you notice, both of these are pointing downward. Well, that's call for trouble because that means we've got an eclipsed geometry. So I'm going to draw my CH3, and I know there's a bunch of stuff hanging off. Just draw what you see. If you see a CH3, just draw it down here. Don't worry too much about depicting it. Just don't leave anything out and don't have any blanks. Okay, so I have an eclipse geometry. That makes things a little bit trickier because now I'm going to have to draw the H that's on the circle directly behind it. So I've added my vertical substituents. Both were pointing down in this case, defining an eclipsed geometry. And when the more eclipse geometries I put on exams, the lower my teaching evals get. I get it. So it's a little bit awkward. Everybody likes the staggered conformation. Me too. Okay, so then we've got to add our remaining groups. I about just drew something. So I've got up and to the right, up and to the left, and I've actually got up and to the right, up and to the left for both the dot and the circle because, again, we have an eclipse geometry. All three groups are overlapping with each other. And we know that because we can see that right away with the vertical substituent because they're both pointing down. Okay, and then I drew the groups in the back carbon so that they were still 120 degrees separated. So now we need to fill in the blanks. We have 4 blanks left, and to do that, we need to remember our rule. If we're looking left, our wedges are on the left, and if we're looking right, our wedges are on the right. So if you look here, we are looking left. The arrow from our eye is moving from right to left. So what that means is that wedges are left. Okay, again, to figure out what is the right side and the left side, what we want to do is we consider a straight line through our vertical substituents if you're having trouble seeing this. I find that with a little bit of practice, students are able to see the left and right side of the Newman projection fairly quickly. But if you can't yet, this is our left side, this is our right side, because we're looking at a front end perspective of a Newman projection. Okay, so we have left and right side. We're going to add, excuse me, our wedges on the left side. So the wedges are going to be H attached to the dot. That's going to be this guy, these two guys. And then we've got OH, which needs to go here as it is attached to the circle. OH to the circle. And then the dashes get added to the right side. Again, we're looking left, so our wedges are on the left. The remaining positions are our dashes. And we've got a CL that's connected to the dot and an H that's connected to the circle. So we're going to go CL and H. You just draw what you see. Don't make it too hard. Okay, so that was a pretty difficult example, I would say. I'm not really throwing us too many cupcakes in these examples, so hopefully this is helpful. One oddity that I could do is I could say, let's say that I hand you this molecule, and I say, draw a Newman projection analyzing free rotation over this bond. So we're going to analyze this carbon-carbon bond. Now, if I do that, that's a bit awkward. You need to draw the seesaw structure. Okay, so seesaw structure is always carbon-carbon with the bond connecting the two parallel to the bottom of the piece of paper. And now this becomes a choose your own adventure. You pick the wedges and dashes. So seesaw structures are going to have a wedge and a dash at both carbons along with a straight line. I like to pick staggered conformations because they make easier Newman projections. So I'm going to put my lines on opposite directions. That's going to be a line up and a line down on either side, so that we get a staggered conformation. Then we have wedges and dashes. So we pick the wedges and dashes. What does that mean? Well, what's connected, this bond of interest needs to be the bond that's separating the two carbons in our seesaw structure. If you look at this purple carbon, which maybe we'll just leave right there, it's only got one group attached to it, right? It's an OH. Let's go ahead and put that in the vertical position where it's easiest. What else is added here? Well, we don't have to draw it, but there are two hydrogen atoms. So there are two hydrogen atoms that are drawn there. And you're like, why didn't you just write them out explicitly? Well, remember, the rules of bond line structures say that we don't write those hydrogens. So they exist, their existence is implied, they are implicit hydrogens. We need to include them in our seesaw structure because we need to show a position for all the wedges, dashes, and straight lines. But in our bond line structure, we don't need to include them. Okay, what about the other half of our seesaw structure? Whew. We've got this big hulking thing. Well, that big hulking thing is just a hexagon. So let's not make it more complicated than it needs to be. Let's just draw a hexagon, a little bit of an awkward angle. And then once again, we have two hydrogen atoms. Their existence is implied. We didn't draw them with the bond line structure, but we do draw them in our seesaw and Newman projections. Okay, so there's our seesaw structure. Now we're ready to add a dot with a circle around it. Let's put our eye on the left side of the molecule and have it look from left to right. So we're looking right. We're looking right. Now we're going to have a dot with a circle around it. The first thing our eye bumps into is an OH pointing down. And then it goes into the next vertical substituent, which, ooh, that's a big thing hanging off of the molecule. Well, it's just a hexagon, so let's not make it more complicated than it needs to be. We're not analyzing the hexagon. We'll do that for the next exam. That's going to define where the remaining positions are. And then in this case, everything is just hydrogen, though we could look right to make sure that we added these hydrogens first if we wanted to the right side. But because they're all the same, it doesn't matter. So there are two examples of drawing Newman projections from seesaw structures. In the second example, along with the one with all the variables, along with an example where I didn't even define the wedges and dashes, I just gave you the bond that I wanted you to analyze. Being able to go from the seesaw structure to the Newman projection is a big step forward. And it's really not as bad as it appears once you get going and kind of remember some of the mnemonics, like starting with the vertical substituents. Looking left means wedges on the left, looking right means wedges on the right, that sort of thing. It all starts to come together, and you can move through these things pretty quick. It's more than half the battle, but the other thing we do want to look at, which we'll look at in the next video, is going from a Newman projection back to a seesaw structure.